the idea is we wish to, well, optimize, right? So that means maximize or minimize some objective function. So this is a fancy word, I guess, objective function. But basically, when you see those two words together, objective function, you want to think, oh, maximize or minimize it. That's the whole deal. There's something we want to maximize or minimize. Okay? So I thought it might be nice to imagine that what we're going to do is we have some, well, let's do this. Let's create, I want to talk about surface area. Oh, well, before I do the surface area thing for objective function, I'm going to say this. I'm going to say many times we are maximizing subject to some constraint. There's another vocab word, and I'm going to put a little S here because you might have more than one constraint. Okay. So my example I thought I would do is going to be a minimization problem. I'm going to try and show you how we can minimize the surface area of an open top box. Okay, so what do I mean by this? I guess I'm picturing, you know, we're going to build a box. Like this. And so when I say open top, okay, so you could see inside, right? It goes down. So we're you know, we're trying to use some kind of a material and build this box. And so I guess what I can do is I can say that this is X and this is Y and then maybe this is Z, right? And what I could say is, well, I could say that we're going to minimize the surface area of an open top box. Let me continue this way and say, subject to the constraint that we want it to hold some volume. We want the volume to be, I'll just say some constant V. I mean, when you actually do the homework problems, they'll probably give you a number. Okay? So maybe they'll tell you, all right, guys, we have some material, we're going to fold it up and make an open top box, and we want it to hold, tell me how much volume. Well, I guess if I'm measuring in inches, right? So I could say it's 32 cubic inches. Or maybe that's way too small, maybe 2,500 cubic inches. Or whatever it is, right? Whatever it is, I'm going to call it V. Okay? So this is the constraint, right? The thing I'm trying to minimize right here, right? My objective function, okay? So I'll write that in black. Objective function would be S for surface area. S is equal to what? Well, I guess it's, yeah, what would be the surface area of this box? Yeah, I mean, we have different size pieces, right? Like the front is XZ, and the back is XZ. The bottom is XY. So you could say it's XY plus 2XZ plus 2YZ. There's my surface area, right? The only reason there's not a 2 there is because there's no top. The constraint that I was given is that we want the volume to be constant. So my constraint would be x times y times z is going to be that constant v, right? Because we know how to find the volume of a... So the way it worked in Calc 1 was this. If you wanted to do this problem, you needed to have enough constraints to substitute in here. But now that we're in Calc 3, we don't necessarily need that anymore. That's kind of the idea, right? So, for example, I could solve for z. I could say, well, I know that z is equal to v over xy. And then what can I do is I can substitute. But what's going to happen here is I will have surface area now is a function of x and y. And that's the best I can do with what I know about this problem. I can't do much more. Where the z used to be, I'm going to plug in my v over xy. And then I have plus 2y times v over xy, right? And so, again, since v is a constant, let's write s of xy as xy plus, since v is a constant, I'll bring that out front. I have 2vy, because the x's cancel, right? Plus 2v, wait a minute. Oh yeah, the y's cancel. So let me think about that. Right, these would be y to the negative 1 power, right? Because the y's cancel, and x to the negative 1 power, because the y's cancel. Okay. So yeah, maybe writing it over y would be better. But now what we want to do is we want to find critical values, right? And so to find critical values, here's where you want to find partial derivatives. We did this in class last week on the group work, right? So let's see, I'm going to do Sx, I'm going to do Sy, those partial derivatives. So Sx, what would that be? I guess it would be, well, we're treating y as a constant, right? So it's going to be y, and then when I treat y as a constant here, this just becomes 0, right? So y plus 0, and then what about here? I guess I get minus 2v over x squared. Is that okay? Or 2vx to the negative second. Depends on how I want to write it. Okay. And so then sy is going to be x minus 2vy to the negative second. So there are Sx and Sy. Okay? And so we're going to set our, if we set those two equations equal to 0, we can find what? Yep. And we can find the critical values. Okay? So that's kind of one of the things to do next. I'm going to compute a few more derivatives though first. Okay? I'm going to compute the second derivatives, the second partial derivatives. Because just like in Calc 1, how the second derivatives were important for this kind of problem, same thing's true here. Okay? So let's do a couple more computations. Let me compute Sxx. So that would equal, well, 0 minus 2v and then times negative 2. So I'm going to get 4v x to the negative 3. Does that make sense to you guys? Okay. What's another partial I can compute? Well, SYY would be what? 4v y to the negative 3. But then there's other ones you can do, right? So you can compute Sxy, and that means take this first function, but take its partial derivative with respect to y now, right? So we computed the partial derivative of s with respect to x. Now take this partial derivative with respect to y. What's that going to equal? 1. Because it's 1 plus 0, because there's no y's there, right? And by the way, one of the facts we went over last week was that usually this is going to be exactly the same as syx. And is that true in our case? You can see it. Okay, so I'm telling you that those partial derivatives will become useful for us when we do optimization. All right, let me switch the page anyways. Let this thing bounce back. And what I want to do next, okay, is I'm going to set ds dx equal to 0 and ds dy equal to 0. Those two that I found. So Sx, the partial derivative with respect to x, was, well, okay, it was y minus 2v over x squared equals 0. Right? And then I should point out also, where are these partials ds dx and ds dy undefined? That's the other thing I should think about. So these are all going to be called critical values, right? Where is this thing going to be undefined? This is going to be undefined when x is equal to what? 0. Or the other one, of course, we had, the other one was very similar. It was x minus 2v over y squared equal to 0, right? So the other one is y equals 0. So these, we already have a bunch of critical values. If x is 0 or y is 0, those are critical values. But we're also going to get critical values here. Okay? So let me solve these equations. When I solve, I get x squared y minus 2v is equal to 0. And here I get, oh, xy squared minus 2v is equal to 0. Not quite the same equation, but close, right? I get a system of equations. I have two equations, and how many unknowns do I have? 2. So I'd be able to solve. I mean, I have that x squared y is equal to 2v from this equation, and I have xy squared is equal to 2v from this equation. Oh. So you know what must be true? I guess in this situation, I can say that x squared y is equal to xy squared, right? This is kind of a substitution I'm making. How do you solve an equation like that? X equals Y? Let me try this. I mean, I guess you're right. So, because if we set it equal to 0, right, x squared y minus xy squared equals 0. And if we factor out the common factor of xy, so there's my x equals 0, there's my y equals 0, and the only other possibility is that x minus y equals 0, which means that x equals y, like you guys said. So if x equals y, oh, that says a few things. First of all, what's it say about the shape of the open top box? That would be a square. A square box. Of all the rectangles, somehow the square is optimal. Or, the other possibilities, and we already computed that, right? X is 0 or y is 0. Now, if x is 0 or y is 0, either one, I claim that is minimizing our surface area. Well, actually, it's impossible, right? You can't do it. You don't have a box because nothing fits in it.
We take triangles that are just lines.
But we don't put things in those triangles. I guess what I'm saying is I think we should concentrate on that solution. Hey, by the way, do we know how big x and y should be if they're going to be equal? Well, I guess we do in a sense. I mean, if we knew what the volume was, I called it V, you could come back here and you could say, look, x times x squared has to be 2v. So x cubed is 2v. So x is the cube root of 2v. And yes, that's equal to y. Whatever volume is, multiplied by 2, take the cube root, and that's the dimension you need for x or for y. Oh, you know what I don't know? I don't know if this will maximize my surface area, minimize my surface area, or neither. How do you figure that out? In Calc 1, yes, that's something I wanted to get at. In Calc 1, the second derivative test, the way it worked was this: concave up, right? If f double prime was positive, greater than 0, concave up, cup, meant that I had a relative minimum. You guys remember that? F double prime negative meant concave down, frown, meant I had a relative maximum. You guys remember that? Okay. Well, in the world of Calc 3, when I have functions of 2 variables, it's a little more complicated than this, but there is kind of a method that's analogous to the second derivative test, okay? And it's the second partials test. And we did all the computations, okay? So I want to kind of outline the strategy for you here, or at least demonstrate it, because it is outlined in your book. But the idea is, okay, so in multivariable calculus, we compute the discriminant, is what our book calls it. Discriminant. It's also called the determinant of the Hessian matrix. To decide what kind of critical value we have. So I need to show you what that is. and how it works. Now, this thing called the Hessian matrix, for us, it's basically a matrix made up of all the different second derivatives you can compute. Okay? So for us, it's this. Sxx, Sxy, Syx, and S what? YY. You put all the different combinations. Basically, one row is X and one row is Y, and you kind of go through. And you get a matrix. Well, I guess it would matter, except that for us, almost every time, Sxy is going to be exactly the same as Syx. So it's a symmetric matrix, we say, and so I guess it won't matter. It won't matter. Okay? And so what we do is I say that because it's funny, your book gives a definition for the discriminant, but the easy way to remember it is, how do you take the determinant of this matrix? Basically, guys, I'm going to take this product, Sxx, so they call it D. D, the discriminant, is Sxx times Syy, that product, minus the other product, Sxy times Syx. And I think your book actually puts a 2 here, because these are almost always the same. But this is what you have. Okay? So let's write out what that equals. But it is basically always the same, but you're right. You didn't see me do it, did you? Okay. But you're right. So your book...
They don't even mention it, though. Like that's...
They do mention it, but you gotta... How carefully are you guys reading this stuff? It's there, I think. How carefully am I reading it? I'm trying. Another question. Kathy.
I can't get past the order piece because
Yeah?
flipping the order determines positive or negative. I mean, you're going to get opposite. You'll get the same numerical value, but not the same sign.
You will. You will. If I switched the roles of X and Y completely, I would still get the same value for D. I claim that. But you have to maybe try it once to see it. Okay? Yeah, we should fill some of this stuff in. I think my partial derivatives are on the previous page. Do you guys remember what these are? Okay. Sxx, what does that equal? This was 4v over x cubed. Okay. So this was 4v over x cubed. And this was 4v over y cubed. Am I right? And weren't both of these equal to 1? Okay. Wow, okay. So I guess we get, what's it equal? It equals 16v squared over x cubed y cubed minus 1. Okay. So now the way that concave up and concave down was decided was based on the sign of the second derivative. Was it positive or negative or 0? Okay. And I'm going to show you the little chart in the book now that they have for this. It really comes down to, the first thing you ask yourself is the discriminant positive or negative or 0? Here, maximum and minimum problems on the right-hand side of our screen, right here. Where do they say second derivative test? Here we go. Dun-da-da-da. Scooting along. Oh, yeah. I'm coming back to this picture in 1 minute. Okay. If the discriminant is greater than 0 at a certain point, good things happen. If the discriminant is less than 0 at a certain point, F has what's called a saddle point. And then I want to point out step 4. Look at option 4. If the discriminant at a certain point is equal to 0, tough luck. Okay? We had that in Calc 1 also. If the second derivative was 0, it wasn't concave up or concave down. Okay, so there is the tough luck possibility. Let's see what happens in our problem. In our problem, what did we say the critical value was? Oh yeah, I have it up here, guys, right? In purple, I have x and y are both equal to the cube root of 2v, right? So what I can do is I can plug that into my formula, and I can say our value of d is 16v squared over, now when I cube the cube root, it goes away, right? So it's just over 2v times 2v, and then I'm going to subtract 1. So what do I get? 16v squared over what? 4v squared. The v squareds cancel. Sounds to me like I love this class when I get to write this on a Calc 3 problem. 4 minus 1 equals 3. The key is it's positive. It's positive, right? So let me go back to my chart. My chart says, which case am I in? Either 1 or 2. I don't know which. Not 3 and not 4. So I have a positive number. It says, at this point, guys, look at fxx. If fxx is negative, you have a local maximum. That might not surprise you because, remember back in Calc 1, when the second derivative was negative, you had a relative maximum. So basically, you have to check, is the discriminant positive? If it is, then look at fxx. And the book doesn't say this, but you could also just look at fyy if you wanted also, from what I understand. But anyways, let's look at fxx. What is fxx? Oh, it's not fxx, it's sxx, right? So I guess I could right here notice that our value of sxx is 4v over what? Yeah, but what's x? X was the cube root of, so it's just over 2v, so it equals 2. So the important thing is it's positive. And if it's positive, that means this, concave up, cup, relative min. And so what did I learn from all this work? I learned that these values will minimize what? So if you take some volume you're going after, but you want to minimize the surface area and keep a constant volume box with an open top, I guess what we just learned is, the rule is, hey guys, make the base a square. You know what I didn't learn yet that I want to figure out? How tall should it be? We can do that, right? How do we do that? We need to compute z. Where did z go? Oh yeah, way back at the beginning, we solved for z with this constraint. Remember that? So let's see what z would equal. Z was v over xy, so it's v divided by the cube root of 2v times the cube root of 2v, right? So what's that? I guess it's v divided by 2v to the 2/3 power. So it's, well, v divided by v to the 2/3 is just the cube root of v. And then I have to divide by 2 to the 2/3 power. So that's the z value. It's not the same, or is it? No, it's not the same as the cube root of 2v. Actually, what I could do, guys, is I could take that and multiply top and bottom by the cube root of 2. So if I multiply by cube root of 2 and cube root of 2 on top and bottom, and here I had the cube root of v, and here I had 2 to the 2/3 power, what I learn is that z should not be as big as x and y. It should be the cube root of 2v over 2. So it should be half as big as the square. So when you have an open top, make z half the size of x and y, and make x and y into a square. That's a cool problem.
It just makes logical sense though.
Well, I like that.
Well, because the shorter box, the
Yeah.
bigger bottom, you're not using as much surface.
You're not using as much surface area. But it's cool that it works out to be a half, I think. It's also cool to see just, I think, a hands-on example of all this machinery we have at work. Okay? And one other thing would be, I ought to at least show you a picture to show you the other possibilities, right? Because it could be that the discriminant is negative, and it says that f has a saddle point. What does that even mean? They give a pretty nice picture, and they also give a nice explanation. This picture shows why it's called a saddle point. See where the blue and red intersect? So is that a maximum or a minimum? And the answer is no. Right? It's not. I mean, in the y direction, it's right. In the y direction, you could say it's kind of a maximum, but in the x direction, it's kind of a minimum. And that's called a saddle point because you can imagine this is the saddle of a horse. But then what you really realize is we need to define it more precisely than just it kind of looks like that, because it doesn't have to. There's other ways it could look. Basically what you need is if every open disk that you could possibly draw around the point will have some points lower and some points higher, then that's what negative discriminant indicates. We call it a saddle point in this book, because maybe the most basic example is what I just showed you. Okay? So, wow, we're at break time. I hope that was enjoyable.